Okay, so 28 is kind of a weird one because it challenges some of the concepts that we have learned. So if you take a look at it, it actually gives you the boiling points. Typically, the questions for intermolecular forces ask you, hey, like, estimate the relative boiling point, right? Which one's higher, which one's lower. So if you take a look at ethanol, based on what we learned, you would kind of assume that ethanol might have a higher boiling point, right? If these weren't given to you. Okay, what type of intermolecular forces does ethanol experience? Yeah, hydrogen bonds should be the one that really pops up for you. I mean, that also means it includes dipole, and dispersion. But if you take a look at octane, what's the strongest intermolecular force that this one experiences? Not dipole. So this is only dispersion. Okay, this does not experience any type of dipole because if you look at it, this is nonpolar. Okay, this is a nonpolar molecule. Easy way to remember that is it's only made of carbon and hydrogen. Hydrocarbons are notorious for being nonpolar because carbon and hydrogen have about the same electronegativity. So there's no pull anywhere in this molecule. So this is a nonpolar one. So the only thing it can experience is dispersion, which means that the only way to get a temporary dipole is for the electrons to just randomly congregate on one side of the molecule. So it's random, so it's not that strong typically. All right, so that's what we talked about before. But for this problem, again, I said it kind of challenges what we've been learning because it gives you the boiling point. So if you take a look at the problem, it says ethanol has 78 degrees Celsius, while octane is 125. So we know that hydrogen bonds are stronger than dispersion, but according to the problem, which one has a stronger intermolecular force within the substance? Yeah, octane, okay, which is kind of different than what we've been talking about. Again, dispersion is typically weaker than hydrogen bonds, but here it's telling you octane is going to have a stronger intermolecular force keeping it together. So it gives you 4 possible explanations, and you got to figure out why that is the case. So A says octane experiences hydrogen bonding. We just talked about it does not experience hydrogen bonding, right? It doesn't have the HO, HN, or HF polar bond, right? It's just CNH, so A cannot be correct. If you take a look at B, octane has significantly higher molar mass. Okay, and this is true. Okay, but this is actually the second best answer. Okay, and the reason why is because it does have higher molar mass, and that leads to stronger dispersion forces. But the molar mass itself is not the explanation for the boiling points, because then we can just assume anything that's really large will have a higher boiling point. So the answer is going to be C, because this is the explanation for C. Okay, because it has a higher molar mass, it's going to create a stronger temporary dipole. Just remember, the boiling point depends on the intermolecular force, and the temporary dipole is what explains the boiling point. And the molar mass is a reason for the temporary dipole. Yeah. Yeah, temporary dipoles are where you have a molecule like this, and we talk about how the electrons move somewhat randomly, right? So they fly around, and so if they happen to randomly congregate on one side, right, just by chance, that creates a temporary dipole. It'll be partially negative, partially positive, because they just happen to be there. So it's temporary. It's not permanently like that. An example of a permanent dipole is, again, water, because oxygen is so much more electronegative. It will always permanently have a dipole on this side, but here it's random, so it's temporary. It can move to that side and then move to the other side. Great question. And then symmetry doesn't have to do with affecting the intermolecular force. So if you put B, that's actually the second best answer. You just didn't identify that molar mass is not what explains boiling point. Molar mass explains the temporary dipole, and that explains the boiling point. So honestly, if you got B, that's not a bad answer. It's just that C is a better answer. Okay. All right. Any questions? Okay, so that's intermolecular forces. Nice way to start off, since that's what we talked about last class. Let's go to 29. 29 gives you 2 ionic compounds, calcium chloride and calcium oxide, and it's asking you to predict which one has a higher boiling point and why. Now, before you do this, I want you guys to try it on your own. I do want to give you a little clue to kind of help you. Take out your AP equation sheet. If you take a look at the Coulomb's law formula, the one that we talked about last time, this is actually going to help you find the answer for this problem. Okay, Coulomb's law. We said that Coulomb's law explains to us the attraction or repulsion between two bodies. Q is the charge of one of them. Q2 is the charge of the other one, and radius is the distance between the two. Okay, so that's my big hint for you. It'll help you get your answer. But basically, you're trying to figure out, using Coulomb's law, why one of these has a higher melting point than the others. Take about 3 minutes. See if you guys can figure it out. If you can use Coulomb's law, it should help you with the explanation. And it should make it very clear which one is not a good option. Okay, so take about 2-3 minutes, and then we'll go over it together. All right, so first let's use Coulomb's law for CaCl2. Okay, so if we take a look at it, let's do calcium. What is the charge on the calcium ion? Yeah, +2. What's the charge on the chloride ion? Yeah, -1. And then we'll just leave R just there for now, okay? So that means that you will get something around 2 over R squared, okay? All right, let's do the same thing, but this time we will do it for Cal. Okay, what the charge on calcium is still +2. What's the charge on oxygen though? Yeah, -2. Okay, and then R squared. So if we simplify it, oh sorry, I forgot to put a negative sign up there. Okay. If we simplify it, it'll be -4R squared. Okay. So just by looking at that, you can kind of estimate what's going to have a stronger force, right? Obviously, it's going to depend on the radius, but just at face value, what do you think will have a stronger attractive force? Yes, CaO, and it's because of this right here, right? The second the anion's charge. Okay, oxygen is going to have a greater charge than the chloride ion. And so that kind of gives you your answer. Your answer is going to be C. Okay, but let's talk about why the other answers are incorrect as well. But does that make sense generally?
Yes.
Okay. If you also took the radius into account, it would actually further support your answer for C. Because if we use Coulomb's law and we take into account the radii, let's take a look at oxygen and chlorine. Okay, so if you take a look at it, which one is bigger, oxygen or chlorine?
Chlorine.
Yeah, chlorine is a lot bigger, right? Because it has a third shell. And so we talked about this last time, but if you have a bigger number on the denominator, what does that do to your actual value? Yeah, it decreases. So if you increase the radius, that means that the Coulombic force is going to decrease, right? Because it's further away. And so that actually supports your answer more. The radius of chlorine actually makes this number even smaller than this comparison. And since oxygen is smaller, it makes the attraction even stronger. Okay, so you could have looked at either the charge and the radius supports your answer even more. Okay. Yeah. Yeah, there is, but you're not going to be expected to find it. Typically, they'll give you like a table. I'm sure you've seen a table with like angstroms on it, the A with the circle on top, that variable. Typically, they might give you a table where it says this is the radius of the atom or the ion. Start comparing the two. Yeah, but you'll never have to like calculate it on your own. Yeah. Great question. All right, so let's go through the other options, talk about why they're not correct. A says it's calcium chloride, and we know it's wrong because it's calcium chloride, but the reasoning also doesn't make sense. There's more ions per lattice unit. Basically, it's saying that because calcium chloride is made out of 3 ions, Cal is made out of 2 ions, that means that this should be stronger. Well, we know that just because you have more ions doesn't mean it's going to affect the attractive or repulsive force, so that doesn't even make sense. The number of ions in the lattice or the ionic compound doesn't affect Coulombic force. All right, B is wrong because we just talked about chlorine is bigger, right? So this says chlorine is smaller, so this is the worst answer because it's factually untrue, the reasoning. All right, and then we look at D. It says the common charges of calcium and oxygen are identical in magnitude, which is true, +2 and -2. The magnitude is identical, but that doesn't really affect Coulomb. Okay. Because you're not comparing calcium and oxygen, you're comparing calcium and chlorine. So it's comparing the wrong ions with one another. Okay. So that's the reason why the other three are incorrect. So for this one, there's actually no best second answer. Okay, there's just a best answer and a worst answer. The worst answer is B. So for 30, it's going to be fluorine. Anyone want to share the reason why? Yeah. Exactly. You guys are so awesome. Okay, 5s for everybody. Most electronegative. Okay, so even though xenon is a noble gas, we know that noble gases typically do not form bonds. It can form a bond. First, let's talk about why. How come xenon is able to form a bond to begin with? Yeah.
Because it's far away from the...
Exactly. Xenon is a big boy. It has a lot of shells. The valence shells are really far away. What row is that? Row 5? Yeah, so it's going to have 1, 2, 3, 4, 5. So valence electrons will be very, very far away. Fluorine comes along. Fluorine is very electronegative. It is able to force xenon to share even though it's a noble gas. Fluorine is a bully. It's very strong. It could force people to share. Okay, lithium. Let's talk about the other options. How come lithium can't form a bond? What does lithium want to do with its electrons? Yeah, it wants to lose its electrons, so it's not going to want to try to bond with it, right? Xenon doesn't even want to accept it, so they're incompatible. What about argon? How come argon's not going to be able to form a bond?
It's a noble gas.
Exactly. It doesn't want to form a bond to begin with. It's also a noble gas. And then we look at carbon. I guess carbon would be the second best answer, but carbon is also pretty not very electronegative, so carbon does not work either. Fluorine, though, we know it is the most electronegative element, therefore it is the most likely to bond. It's not for sure going to bond, it's just most likely. Yeah. Yeah, it's like XeF2. Yeah. I think. I'll have to double check on that, but I'm pretty sure it's that. Alright, everybody good with the reasoning? Okay, that one's pretty simple. I'm glad you guys remember. Let's move on now to pH, right? Unit 12, acid-base equilibrium. Okay, but it's the easy part, not the titration stuff or the equations. It's just pH. So it tells you that stock nitric acid, HNO3, has a concentration of 15.8 molarity, super duper strong. And then it's asking for the pH. Okay? So before we start, let's talk about nitric acid. What is special about nitric acid? Ooh, that's 5s for everybody. I'm expecting it now. Okay, strong acid. If you guys don't get a 5, I'm going to go in during the summer and drop everybody's grade by a letter. Because, I'm just kidding. That's illegal for me to do, actually. Anyway, all right. So strong acid. So what is this? What is the most standout characteristic of a strong acid? It is low pH, but more than that, what's the
Weak conjugate base.
Yeah, weak conjugate base. But what does that mean?
Weak base.
Yeah, all of it is gonna dissociate. Okay, so it's gonna be 100% dissociation. Okay, remember weak acids, right? So if you have a weak acid, I don't know, let's say HF. HF is a weak acid. It goes into equilibrium, right? With H plus and F minus, so it's gonna go back and forth. But strong acids like nitric acid, 100% dissociation, no equilibrium. It just goes one way. Okay, it breaks up and it never gets back together. Okay, that's how their love story ends. You put them in water, they break up. They don't get back together. These guys are the wishy-washy ones. They break up, they're back together, break up, back together, but strong acids do not. All right. So that gives you, and the reason why they do that is so that you don't need to calculate the Ka values and whatnot. You don't need to do an ice table. Because if this has a concentration of, if nitric acid has a concentration of 15.8 molarity, what's the concentration of the protons?
15.8.
15.8, exactly. It's the same. But if it was a weak acid, you would have to use an ice table to figure it out using the Ka value. All right, so for pH, if you guys remember, pH is negative log of the concentration of H+. Let me give you guys a minute, see if you guys can plug that into your calculator, get some calculator practice, and I want you guys to get your answer. Alrighty guys, answer should be A because you should get about negative 1.2.
Yeah.
Okay, cool.
So I didn't say my good.
Okay, so it's telling you that there is gravimetric analysis experiments. Basically what you're doing is you're using gravity to filter out and separate different compounds. That's what this means, okay? All right, so it's basically saying that you collect a precipitate. So an easy, like something that we're familiar with is if you have like coffee, right? And you put a piece of filter paper, you pour the coffee in, and then the precipitates get stuck here, right? This is kind of like what you can think of it as. It's like you got a compound, you pour the solution in there, you separate it, and you have this precipitate left over. Okay, and then the solvent gets stuck and then just goes down, but you get the precipitates here. And then what it tells you is that these precipitates that you collect, they rinse it with distilled water. So they use water one more time to basically wash it. They clean it with water. And the question is asking, what is the purpose of doing so? Okay. All right, I'll just give you guys the answer and I'll give you the explanation for why the other ones don't work. The answer is going to be B. It's to wash away any spectator ions. Okay. Okay. So let's talk about what that means. So we talked about net ionic equations, complete ionic equations, and whatnot. Basically, if you have ionic compounds that react with each other in a solution, so let's say I have ionic compound 1 plus ionic compound 2, right? It can make a precipitate. It's going to make your solid, but it could also make some ions, right? So plus or minus ions. So let's say it was like I2+. And this does not form a precipitate. And then you'll get your anion as well. Let's just say 2-. Okay, so these are your spectators. And they're called spectators because they don't do anything in the reaction. They start dissolved and they stay dissolved. Okay, well, when you run them together, there are instances where these spectator ions can get stuck to these precipitates, these salts. Okay, and so the water is able to wash them out because if you remember, water is polar, right? So water can, if you pour water through it, the partial negative of the oxygen will pull this out of the precipitate, the partial positive will pull this out of the precipitate, and that way you get a purer substance. Okay, and so that's why you wash it away. Okay, the other ones, they just don't make a difference. Adding water doesn't, while it's already filtered, does not make the reaction go to completion. That's already done before you filter it. Precipitates don't need to be hydrated. Typically, you don't want it to be hydrated because there's impurities, right? Water is an impurity. And then washing the precipitate does not change. It actually makes the density more incorrect because you're adding water weight, which is not what you're trying to filter out. You've already filtered out the water once. The water is just trying to get rid of the spectator ions. Alrighty, guys, let's go over 33, and then I'll give you some time to study on your own. So it tells you that you got this equilibrium in a container. Now, one of the key things to identify here is that everything is a gas, right? So basically, you have kind of like a balloon, and you got a gas with this equilibrium going on inside, okay? All right, and then what it tells you is that you put some neon gas inside of the container as well. And then it tells you that it does not react with anything. It's because it's a noble gas. And then it asks, what effect will this have on the reaction quotient? So let's talk about what reaction quotient is, and before we talk about the reaction rates. But reaction quotient is represented by Q. And if you remember, Q is the ratio not at equilibrium. Okay? So the ratio between the products and the reactions when you are not at equilibrium. So basically what you're trying to figure out is how does adding Ne affect this ratio, the ratio of this stuff right here, okay? So let's talk about what happened. So in the beginning, before you added neon, you were at equilibrium, right? So you had a specific Kp value. Okay, and the Kp value depended on the products, the pressure of the products divided by the pressure of the reactants. Okay, and remember, gases, we talk about pressure when we talk about equilibrium. So let's talk about what neon does to the pressure. Okay, so if I add some extra gas into the container, what happens to the pressure? Yeah, so the first thing that happens is the pressure is going to increase, right? If I add neon, so if I add neon to my container, first thing that's going to happen is the pressure is going to increase. Okay, does that make sense? Okay, that's pretty easy. You put a gas in a container, more gas in a container, pressure goes up. Now, we know by the chandelier principle, okay, and make sure that when you take the AP test, you don't call it the chandelier principle, it's Le Chatelier's, but yeah, I don't speak French, so chandelier principle. We know that chandelier principle does the opposite, right? Because you swing the pendulum one way, it wants to swing the other way to reduce the disturbance to equilibrium. So chandelier principle tells us that if the pressure goes up, what does it want to do with the pressure? Yeah, it wants to decrease the pressure. So it wants to decrease the pressure. All right, so let's talk about how it can decrease the pressure. If you take a look at our equilibrium equation, let's look at the gases. How many moles of gas are on the reactant side? Yeah, 2 moles. Okay, and how many are on the product side? 3. So just based on our equation, what has more pressure, the reactant side or the product side? Yeah, the product side has more pressure. Okay, so if the system wants to decrease the pressure, which way is it going to shift equilibrium? Yeah, it's going to shift it to the left. So the system wants to decrease the pressure, so it's going to shift equilibrium left. Okay, and we know left is reactant side. So if you shift the equilibrium left, you're going to have more reactants. Okay. So that means the denominator is going to get bigger for Q, right? So if the denominator gets bigger, what's going to happen to Q? Is Q going to get bigger or smaller? Yeah, Q is going to go down. Q is going to get smaller because the denominator gets bigger. So more reactant means bigger denominator. And I'm sorry if I'm being super into the weeds with this. I'm over explaining. It's because I'm just trying to make sure you get my thought process. Q is going to decrease. So that's going to take out all of our answers except C. And the explanation makes sense. Forward rate is going to decrease because you want to go backwards. So that means that the forward rate is going to get smaller. So your answer will be C. Yeah.